Okay, hello and welcome to the lecture for week 7 of my Philosophy of Mind course that I'm running at LaGuardia Community College. My name is Dr. Richard Brown, and this is the lecture for the 7th week. We'll be talking about epiphenomenalism, causal closure, and quantum mechanics. Now, it may seem like these three things don't have much to do with each other, but interestingly enough, they do. So, it's going to be a little bit of a journey here, so sit back and buckle your seats. Now, I want to begin by talking about a guy named Thomas Huxley, and he lived from 1825 to 1895. He was a very well-known person in the 19th century, and especially after his debate had at Oxford University with a guy named Wilberforce, I think it was, which they had in October. Was it October? June. I'm sorry, June 30th. I don't know. It's a very famous debate. You could Google it yourself. So it was in 1860, and he was an early defender of Darwin's theory of natural selection, which had just come out in the 1840s or something like that, I think. And so Huxley was an important defender of that view, early adopter of the view, and a well-known popularizer of it. Referred to as Darwin's bulldog for his vigorous defense at this Oxford University debate. So that's kind of interesting. As we'll see, not only during this time do we have important work being done by Darwin, natural selection, by people in physiology, as Huxley is going to take us through, and then also we'll talk about Maxwell and Maxwell's equations, which are also being developed at this very same time. So this is the 19th century, a very active fertile time in this period. Okay, so now Huxley, defender of evolution as he was, held the view known as Epiphenomenalism, which is a very counterintuitive view, one that's Frankie's prancing around here. So she may say hello in a minute. But epiphenomenalism is a view that you might want to avoid if you can. And so that's what we're going to look at. What are the prospects for avoiding it? So generally speaking, epiphenomenalism is the view that the mind may be produced by the brain, but doesn't in turn interact in any causal way with the brain. So that the mind is causally inactive with respect to the physical world. It doesn't produce any physical events. That's epiphenomenalism, technically. And the word comes from medical sciences, as befits someone like Huxley, who was working primarily within that field. And an epiphenomenon there is, the product of a disease, but doesn't have any useful role, something like that. So analogies are often thrown around, like the steam from a steam train. The steam stack is blowing smoke, but that smoke doesn't make the engine do anything. It doesn't have any causal role. It's produced by the functioning, but not doing anything. And so, in a rough sense, that is Huxley's view. We're going to look at the basic way that he puts it is that human beings are conscious machines, conscious automatons, as he says, actually. And what he means by that is that the human body is a machine. He thinks this is something that science is revealing, and we'll say more about what that means in a second. And that brain functioning produces consciousness, but that consciousness in turn does not do anything to the brain. So that's Huxley's solution to the mind-body problem, that somehow even if the brain is causally doing stuff and as a byproduct it has this result of consciousness, there is no in turn effect back onto the brain. Now, that's an extremely strange view because at first, again, everybody that we were talking about last week was trying to explain how the mind and the body interact, and they were led to these weird views like parallelism. That's a weird version of epiphenomenalism. No interaction whatsoever. One would like to avoid that view. So here we find Huxley arguing for it. And one thing that I do in my classes, in the classroom, which I haven't yet been able to bring to the online component yet, is doing close readings of key texts. And I think that the Huxley piece is a good candidate for that. And the reason is that Huxley's a great writer. It's very clear. It's written in modern English, so I think it makes a lot of sense. But he was also a great orator, a great debater, so he knows how to put a point. And I think that if you're going to look to someone who's serious about epiphenomenalism, Huxley is about as good as you can get. So I want to go through it. There's several of these slides that have text from Huxley's piece, and the article is called "On the Hypothesis That Animals Are Automata and Its History." And this is roughly the idea that starts with Descartes. So we talked a little bit about this brief in the Descartes section, but it's always one of the fascinating parts of talking about Descartes is his view that animals are just machines that do not have conscious experience whatsoever. So Huxley wants to defend half of that view, that animals are machines, but he wants to deny the other half, that they have no conscious experience whatsoever. So he's going to say, look, just like animals are machines with consciousness, so also human beings are machines with consciousness. He's going to make this kind of argument. So let's take a look at what he's doing here. So this is his way of setting it up. He says, quote, Descartes' line of argument is perfectly clear. He starts from reflex action in humans, from the unquestionable fact that in ourselves, coordinate purposive actions may take place without the intervention of consciousness or volition, and even contrary to the latter, like against what you want to be doing. So now reflexes are, of course, a great place to start. And this is where Descartes does start. And so Huxley's reminding us that this is right. And Descartes was really interested in physiology. He did a lot of work trying to, he knew a lot about the connections between the brain and the muscles and the nerves. He was very interested in that stuff. And so this is an important starting point for them. It looks like human beings are able to do things that don't involve consciousness, where consciousness isn't producing the action. Remember, that's the goal here, is to establish the claim that maybe consciousness doesn't produce actions like we think it does. So he says, well, at least sometimes it does that, and reflexes are clear. And of course, there's the patella reflex where you bump the knee and it goes up. But there are other reflexes, like if I were to throw something at your face, you would probably blink or throw your hand up, and that seems really reflexual. Doesn't seem like a lot of thought has gone into that. Doesn't seem like action is being guided by consciousness there. And so, but it's purposive. Your purpose is to block the thing that I threw at you. So it looks like there's a purpose to it. Looks like it's done on purpose with intention, but it doesn't seem to be controlled by consciousness. So then, starting from the fact that it happens sometimes, there's no absurdity in saying it happens all the time. So he says, quote, as actions of a certain degree of complexity are brought about by mere mechanism, why may not actions of still greater complexity, be the result of a more refined mechanism? So he's saying, look, the mechanisms that produce these reflexes may be simple, and the patella reflex is studied as because of its simplicity. It's a couple connections, a couple of neurons. Inhibitory, excitatory, bam, kick. Very simple. But that doesn't mean that every mechanism has to be that simple. Why couldn't there be a more complicated mechanism producing more complicated actions? So this is classic Descartes strategy here. You start with something that's ordinary, commonplace in our experience, and then you sort of generalize from that. What if that were happening all the time? How do we rule that out? You make a mistake when you add up some numbers. Okay, well then maybe we could be wrong about everything we add up. You judge that something is straight when it really is bent. Okay, well maybe we could always be judging it incorrectly. Sometimes purposeful actions are done without consciousness producing them. Okay, so maybe they can always be done without consciousness producing them. So I think that this beginning point here is where Huxley is making the conceptual, not impossible claim. Whether it's an actual occurrence or not, whether or not epiphenomenalism is true, we can see that, it's just basically a generalization of reflexes. More complicated mechanisms producing more complicated behaviors. There's nothing conceptually absurd about the idea that behavior is produced by the physical mechanisms in the absence of consciousness. Okay, so moving on to the next stage of the argument that Huxley wants to set up. He says, quote, "It must be premised that it is wholly impossible absolutely to prove the presence or absence of consciousness in anything but one's own brain, though by analogy we are justified in assuming its existence in other people." So right there, is a statement of the problem of other minds, which in the early 1900s, 1950s, and so forth, philosophers were obsessed with. Excuse me. Excuse me, I'm still sick. And so drinking my water, trying not to cough on you. I know it's just through a microphone, but you don't want to be coughed on. So the problem of other minds was thought to be extremely difficult. The question is this: if it really is true, like Descartes suggests, and which people seem to find intuitively plausible, that your own mental life is private, and where what it means to be private is that only you get to know about it, and in a real sense, I can't know about it because I'm over here, I'm not experiencing it. You have to be there to know what it's like for you. That's privacy. Notice that's very different than the Nagel thing that we were talking about a couple of weeks ago when we were talking about consciousness, where Nagel was talking about points of view and subjectivity, because according to Nagel, those things are types. And so I can kind of know what it's like to be you. It's kind of like being like me because we have a type. So, roughly similar. Now, I can't know exactly what it's like to be you. That's the privacy bit. But in rough form, Nagel was more worried about like how we know about bats, who are very different from us because they're a different type of experience. Whereas things that have the same or similar types of experience, you can kind of get yourself into their position, so to speak. But that doesn't seem to help with Nagel's problem. That's, of course, a different question. But this is Descartes' problem of the privacy of the mental. And then once you get that far, you've painted yourself into the corner. How do you know anyone else has a mind? Yeah, they behave a lot. But in dreams, there's a lot of behavior. No other people, though. In dreams, lots of other behaviors. I've had dreams of having lectures. I've had dreams about my dog barking, people asking me questions. But there's no dogs or people there. So how do we rule that out, what's going on here now? Now, the most popular answer given at the time that this was worked on was the argument from analogy. Well, you have brains, and so therefore, if brains are responsible for it, they must solve this problem. Okay, so the problem of other minds is a serious problem. How do we know that other people have minds? Is the fact that they have brains good enough to answer this question? We're going to save that kind of question until we get to the brain-centered stuff, the identity theory, which is coming up here. So I just wanted to point out, though, that Huxley sort of mentions this and that's important. Okay, so now this is very interesting, and I want to dwell on it for a second. So let's read this passage here. Again, I could give you page numbers, but you could read it in the book. Or if you just Google Huxley and hypothesis automata, you'll get a PDF of this, which is where I got the text from. So here's what Huxley says. He says, quote, "Now, if by some accident a person's spinal cord is divided, this person's limbs are paralyzed, so far as their own volition is concerned, below the point of injury. And this person is capable of experiencing all those states of consciousness which, in his uninjured state, would be excited." I'm sorry, I misread that. "And this person is incapable of experiencing all those states of consciousness, which in his uninjured state would be excited by irritation of those nerves which come off below the injury." So you get this person, they're paralyzed below a certain point, and they can't feel anything that's going on down there. They report to you that they don't feel anything. He continues, If the spinal cord is divided in the middle of the back, for example, the skin of the feet may be cut or pinched or burned or wetted with vitriol, which is a corrosive acid, without any sensation of touch or of pain arising in consciousness. So far as this person is concerned, therefore, the part of the central nervous system which lies beyond the injury is cut off from consciousness. So he's setting up an argument here. Again, you imagine the person is paralyzed. You burn their foot. They report that they don't feel anything. Okay, so now you've damaged the tissue, and normally doing that would cause them to experience pain, but in this case, you've severed the connection, so there is no experience of pain from the person's point of view. So far, so good. But then he goes on to say, it must be admitted that if anyone think fit to maintain that the spinal cord below the injury is conscious, but that it is cut off from any means of making its consciousness known to the other consciousness in the brain, there is no means of driving him from his position by logic. Now that's very interesting. Think about that for a second. We spent a whole week talking about this question. Can there be consciousness that you are totally unaware of, that you in no way experience? And this is making a similar kind of point. You suppose that someone said, well, look, you cut the spinal cord and then you burn the foot. And there is pain in the foot, someone might say, because, naively, it feels like the pain is in the foot when it's normal. So maybe that's what you might think. Some people have said worse. And you might say, well, look, that pain, it's painful, but you just don't know about it. But it's down there. It's painness down there. Well, that's interesting. And he says it must indeed be admitted that you cannot disprove this. Why? Because, consciousness is private. So maybe there's some private locked off consciousness down there. This is exactly the issue of whether or not you can have consciousness that you aren't aware of yourself as having in any way whatsoever. Now, he says, continuing there, which, by the way, we looked at last week, the debate between Bloch and Rosenthal. This is related to that very issue. It's interesting to see it, though, in 1874, as opposed to the year 2010. Okay, so he goes on, but assuredly there is no way of proving it, right? He said you can't prove that it's false, but you also can't prove it. And in the matter of consciousness, if anything, we may hold the rule, de non apparentibus et non existentibus idem est ratio, which of course, you have to quote some Latin. If you're going to be debating people at Oxford University, then you better come with some Latin. So this Latin phrase comes from legal talk, I think. You might not want to quote me on that, but I'm pretty sure it's a phrase that comes from the law. And roughly what it says, if you were to translate it literally, it says, of the things which don't appear, and of the things which don't exist, treat them the same. They're the same. So what does that mean? The things which aren't there and the things which don't exist, they're the same thing. Okay, so roughly, if you weren't so literal, what you would say is that, look, if there's no evidence for it, then it's not there. Now, that's not always true, obviously. The absence of evidence is not always evidence of absence, and we can grant that point. But Huxley says, if we can hold this rule anywhere, then it seems like consciousness is a good place, because if you really don't know about it, then how is it consciousness? Look, it seems that here is a good place to apply that rule. And I think it's interesting that this issue, which is surfacing up again, is the same issue which Huxley is dealing with here. Okay, so he says, however near this brain the spinal cord is injured, consciousness remains intact, except that the irritation of parts below the injury is no longer represented by sensation. So now he's making the case it's the brain that's doing it, right? You cut the cord at the waist, and you still have consciousness, but you can't feel below the waist. You cut the cord at the chest, you still have consciousness, but you can't feel below the chest. You cut the cord at the neck, You still have consciousness, but you can't feel below the neck. So he's kind of saying, look, here's our system. Here's one reason for saying that consciousness is something that's generated by the brain rather than by some other part of the nervous system. And that's, I think, a kind of interesting way of making that argument at a time in the 1800s before they had electrophysiology, so they couldn't do EEG, and they didn't have fMRI. And so he's trying to make this case in a different way. All right, so I think the point is relatively clear, and he needs this as a premise in his argument, by the way. That's what, he's not just doing this because he likes talking about this spinal cord injury. He's going to make the following kind of argument, that in this case, where there is no consciousness whatsoever, you're still going to see some kind of behavior, and the behavior looks like it's going to be a problem. So here comes a long quote. Okay, he says, quote, "But now suppose that instead of making a section of the cord in the middle of the body, it had been made in such a manner as to separate the hindmost division of the brain from the rest of the organ." Okay, and we've now, I should have warned you that this was going to happen. That we've switched from talking about a hypothetical person to a frog. Okay, and what we've done is taken the frog, opened up its head, and like surgically remove the top part of the brain, the hindmost division of the brain from the rest of the organ. So this is something you can go and do to a frog. And back in the 1800s, they had less animal welfare worries, so you could just, test stuff out like this. And this is something that they did. Science often was done by people at home in this way during this time. Something is very different from now, you might think. Okay, so you get a frog and you chop off the top of its brain. Now you say, oh, that's weird. Because he had just gone through I skipped a passage, by the way. Let me explain a little bit. I skipped a passage where he was telling you that, look, you can take this sort of experiment with a human and do it to a frog. And you can actually sever the spinal cord and then burn its foot. And what you get is the foot like shrinks away, like it curls up, the toe moves. So it's got to be movement that's created without consciousness. And he says, actually, you could go all the way up to the brain. And in fact, cut out part of the brain too, like the top part of it. So he says, suppose that you do this. The frog then is absolutely devoid of any spontaneity. This is basically like a lobotomy for the frog. It sits upright in the attitude which a frog habitually assumes. So it sits there in that little pose. And it will not stir unless it is touched. But it differs from the frog which I have just described. That's the one that had its back severed and he was doing things to its foot. It differs from that frog in that if it is thrown into the water, it begins to swim. Now, obviously, if a frog has its spinal cord severed and you throw it in the water, its legs can't move, so it's not going to swim. But this one just has its brain lobotomized. Basically, the top half of its brain has been cut. And he throws it in the water. It begins to swim and swims just as well as the perfect frog does. But swimming requires the combination and successive coordination of a great number of muscular actions. And we are forced to conclude that the impression made upon the sensory nerves of the skin of the frog by the contact with the water into which it is thrown causes the transmission to the central nervous apparatus of an impulse which sets going a certain machinery by which all the muscles of swimming are brought into play in due coordination. If the frog be stimulated by some irritating body, like if you burn it, it jumps or walks away. So he's describing this frog here, and this continues on the next slide, which is why that sentence runs off there. But what's amazing is you removed part of the frog's brain. You've left all the sensory stuff intact. The frog doesn't do anything. It's still breathing, still blinking, sitting there. If you throw it in water, it starts swimming, doing the frog swim. If you burn it, it hops away. So clearly information is getting in and things are happening, but it's safe to say maybe there's no consciousness because you've removed all of the top part. I think that's supposed to be the argument here. So he says, If the frog be stimulated by some irritating body, then, finishing that thought, it does whatever the regular or complete frog can do. The simple sensory impressions acting through the machinery of the cord give rise to these complex combined movement. Okay? So you say to yourself, yeah. Well, I know what's going on here. You see, it still has consciousness. It still sees things. That part of the brain is there. And you just chopped off the part that allows it to use that stuff or something like that. And so that might be one common sense way of doing it. And now I know that you can't barely read this, but here, let me read it. And you can follow along if you want. He says, it is possible to go a step farther. Suppose that only the anterior division of the brain, so much of it as lies in front of the optical lobes, is removed. If that operation is performed quickly and skillfully, the frog may be kept in a state of full bodily vigor for months, or it may be for years. But it will sit unmoved. It sees nothing. It hears nothing. It will starve sooner than feed itself, although food put into its mouth is swallowed. On irritation, it jumps or walks. If thrown into the water, it swims. If it be put, if it be put on the hand, it sits there crouched, perfectly quiet, and would sit there forever. So he means if you put it in your hand. If the hand be inclined very gently and slowly, so that the frog would naturally tend to slip off, the creature's forepaws are shifted to the edge of the hand until he can just prevent himself from falling. If turning of the hand be slowly continued, he mounts up with great care and deliberation, putting first one leg forward and then another, until he balances himself with perfect precision upon the edge. And if turning of the hand is continued, he goes through the needful set of muscular operations until he comes to be seated in security on the back of the hand. So he's basically describing moving his head, and the frog climbs over onto the other side of the hand. The doing of all of this requires delicacy of coordination and a precision of adjustment of molecular apparatus of the body, which are only comparable to those of a rope dancer, like climbing around an obstacle. To the ordinary influences of light, the frog deprived of its cerebral hemispheres. To the ordinary influences of light, the frog, deprived of its cerebral hemispheres, appears to be blind. Nevertheless, if the animal be put on a table with a book at some little distance between it and the light, and the skin of the hinder part of the body is then irritated, it will jump forward, avoiding the books by passing to the right or left of it. Therefore, although the frog appears to have no sensation of light, visible objects act through its brain upon the motor mechanisms of its body. He's discovered a kind of blind sight in frogs. I mean, so there's one, it's kind of sad. You think about this guy sitting in a room chopping up frogs and then moving them, throwing in water. And you think, what is this guy doing? Well, what he's showing is you can get rid of like basically all of the brain. Anything that the frog can sense is not making it. It's not processing. It's not being used. It's, as he said, it sits there, it starves to death. But yet it can do all of these things, all of these complex behaviors, which normally you would swear required some kind of mind, maybe a simple mind, but some kind of consciousness-y type thing. But here it is in the case of the frog. It looks like Descartes being vindicated. It looks like Descartes is right. And that's what he says. He says, it is obvious that had Descartes been acquainted with these remarkable results of modern research, they would have furnished him with far more powerful arguments than he possessed in favor of his view of the automatism of brutes. Brutes means animals in this case. The habits of a frog leading its natural life involve such simple adaptations to surrounding conditions that the machinery, which is competent to do so much without the intervention of consciousness, might well do all. And this argument is vastly strengthened by what has been learned in recent times of the marvelously complex operations which are performed mechanically and to all appearances without consciousness by human beings when, in consequence of injury or disease, they are reduced to a condition more or less comparable to that of a frog, in which the anterior part of the brain has been removed. A case has recently been published by an eminent French physician, Dr. Mesnet, which illustrates this condition so remarkably that I make no apology for dwelling upon it at considerable length. Yeah, so he's making no apologies. But you see where this is going. So hopefully you're recognizing that you might have been thinking to yourself, yeah, that's a frog. What about, how is this going to apply to humans? Obviously, humans are much more complicated, much more fantastic. Frogs may sit around and hop all they want, and maybe you can convince me that they are mechanisms, you might be thinking, but how are you going to do this for people? Well, he says, sometimes brain injuries produce people that are like the frog. Blind sight is one such example from modern cognitive neuropsychology, but he's going to describe this interesting case. And this is a really interesting case. So let's look at his description of it, and we'll ask ourselves what we think. So he says, a sergeant of the French army, somebody that we'll call F, 27 years of age, was wounded during the battle of, I don't know how to say that, Bazielli maybe, I don't know, by a ball which fractured his left parietal bone. So a ball is a bullet. That's a little, these round musket ball type things. So this is before, modern rifling and carbine. Okay, whatever. So now he ran his bayonet through the Prussian soldier who wounded him. Oh, it's okay, so. But almost immediately his right arm became paralyzed. So he was shot in the face, basically, and he became paralyzed. After walking about 200 yards, his right leg became similarly affected, and he lost his senses. So his arm was paralyzed, then his leg was paralyzed, and then he passed out. When he recovered so he was in a coma for 3 weeks. He was in a hospital. The right half of his body was completely paralyzed and remained in this condition for a year. So right half of his body paralyzed. At present, the only trace of the paralysis which remains is a slight weakness of the right half of the body. 3 or 4 months after the wound was inflicted, periodical disturbances of the functions of the brain made their appearance and have continued ever since. The disturbances last from 15 to 30 hours, the intervals at which they occur being from 15 to 30 days. So the guy sort of has these episodes, as they might have been called in the old days. So Huxley continues, for 4 years, therefore, the life of this man has been divided into alternating phases, short abnormal states intervening between long normal states. Okay? And this is a result of brain damaging. But now look what happens. Again, another long quote. In the periods of normal life, the ex-sergeant's health is perfect. He is intelligent and kindly and performs satisfactorily the duties of a hospital attendant. The commencement of the abnormal state is ushered in by an uneasiness and a sense of weight about his forehead, which the patient compares to the constriction of a circle of iron. So he feels like something is about to happen. He can tell. And after its termination, he complains for some hours of dizziness and heaviness of the head. So clearly this person is aware. They can tell one of their spells is coming on. But the transition itself from the normal to the abnormal state takes place in a few minutes without convulsions or cries, and without anything to indicate the change to a bystander. His movements remain free, and his expression calm, except for a contraction of the brow, an increased movement of the eyeballs, and a chewing motion of the jaw. So I think you can kind of imagine the kind of thing that's being described. The eyeballs are kind of jittery, moving back and forth maybe, and the jaw is grinding away. But other than that, it's not like he falls on the ground and starts starts convulsing or doing anything all that unordinary. So he continues, the eyes are wide open and their pupils dilated. If the man happens to be in a place to which he is accustomed, he walks about as usual. But if he is in a new place, or if obstacles are intentionally placed in his way, he stumbles gently against them, stops, and then, feeling over the edges with his hands, passes on one side or the other. So it sounds like he can't see. And Frankie doesn't like it when people can't see. So you may notice that she is disapproving in the background, growling. This poor guy. So continuing, he offers no resistance to any change of direction which may be impressed upon him. So if you sort of grab him by the arm and turn him to the left, he goes to the left. Or to the forcible acceleration or retardation of his movement. So if you stop him or push him, he just goes with it. He eats, drinks, smokes, walks about, dresses and undresses himself, rises and goes to bed at the accustomed hours. Nevertheless, pins may be run into his body or strong electric shocks sent through it without causing the least indication of pain. You sort of get the idea that science back in this day was a lot more painful than it is now. Still pretty painful, actually, but they have to ask permission to do stuff like this. So they've got this guy in this state. They're shocking him. They're putting a pin in his arm. He doesn't seem to mind. The conclusion being, doesn't seem like there's some consciousness, right? He's not, you burn him, you stab him. He doesn't cry, but he's still going around doing stuff. Okay. Nevertheless, rereading what I just read, pins may be put into his body or strong electric shock sent through it without causing the least indication of pain. No odorous substance, pleasant or unpleasant, makes the least impression, right? He doesn't care. He eats and drinks with avidity whatever is offered and remarks that the sense of touch alone seems, and takes, I'm sorry, I skipped ahead. He eats whatever's offered and takes anything you give him, which these are vinegar, quinine, and I can't really read that one right there, but they're things that you don't want to drink. So they're handing him all kinds of gross stuff. He's just drinking it. And he takes it as readily as water. No noise affects him, and light influences him only under certain conditions. So they conclude that the sense of touch seems to be the only thing that's going on. And indeed, to be more accurate and delicate than the normal state. So he's really good at telling things by touch. Almost exclusively, that his organisms more delicate than the normal state. And it is by means of the nerves of touch almost exclusively that he finds out about the world that he's in. So here a difficulty arises, Huxley continues. It is clear from the facts that we've just detailed that the nervous apparatus, the nervous system, which in their normal state, sensations of touch are excited, is that by which external influences determine the movements of the body. In the abnormal state, but does the state of consciousness, which we term a tactile sensation, accompany the operation of the nervous apparatus in the abnormal state? Or is consciousness utterly absent, the man being reduced to an insensible mechanism? He concludes, it is impossible to obtain direct evidence in favor of the one conclusion over the other. All that can be said, that the case of the frog shows that the man may be devoid of any kind of consciousness. So he's merely making a not impossible claim here. He says, look, here's a guy, he's got brain damage. He goes through two states. One state, he seems normal. The other state, he's in this abnormal zoned out state. He can do stuff, but he's suggestible. You poke him, you burn him, it doesn't hurt him. So now, when you're poking him, when he's feeling his way around the chair, is there the sensation, the conscious experience of pain? Well, we can't rule out that there is. But also, we can't rule out that there's not. In the case of the frog, he says, strengthens the case. You get these kinds of behaviors. They can be done, very complex behaviors. They can be done without seemingly any kind of input. So this could be a case like that. And I'll leave it for us. I'll leave it for us to discuss whether you agree with Huxley. Okay, we're almost done with the Huxley stuff. We just need to put the cherry on top here. So in his mind, he thinks he's established that the mechanism stuff is true. Okay, and that's also true for humans. But he says, I'm not Descartes. I don't believe that animals are mere mechanisms. He believes they're conscious mechanisms. So why that? Well, here's where the evolution stuff really plays the role in his argument. So he says, the doctrine of continuity, which is one of the claims that evolution makes, that there is a common ancestor for all living Earth on life at some point in the chain. We all share a common ancestor. And all of us at some point have a common ancestor with every other thing on the planet. You have a common ancestor with a tree. You just have to go back really, really, really far to find it. So that's the doctrine of continuity, that there is this kind of gradual chain in nature, the fossil record seeming to indicate this gradual chain of things changing over time into different species, etc. So he says the doctrine of continuity is too well established for it to be permissible to me to suppose that any complex natural phenomena comes into existence suddenly. So if human beings have consciousness, he says, look, evolution would teaches us to think that it's got to show up somewhere, because anything that's complex arises out of simpler things which preceded it. That's sort of what evolution tells us. So he continues, and without being preceded by simpler modifications. Sorry. Sometimes it's hard to tell where the commas are when you're reading this old stuff. So he says, the doctrine of continuity is too well established for it to be permissible to me to suppose that any complex natural phenomenon comes into existence suddenly and without being preceded by simpler modifications. And very strong arguments will be needed to prove that such complex phenomena as those of consciousness first make their appearance in human beings, right? So now, maybe if you're of a religious bent, that's an easier thing for you to swallow because God says you're special and gives us consciousness. But if you believe in evolution and you believe that complex things are built out of simpler parts, then something as really complex as human consciousness has to have a precursor. That's kind of the idea that he's making. And then he says, we know that in the individual person, consciousness grows from a dim glimmer to its full light. Whether we consider the infant advancing in years, so he's making a claim that as babies are less conscious and you get more conscious as you grow older, possibly by learning more concepts or developing language and making more distinctions. That's something we talked about in the intentionality and consciousness section, but that's an interesting point there. But then he says, also, though, we see this growing from a dim glimmer to full light when you emerge from slumber or when you swoon, which is pass out. And that is interesting because when you do wake, it does sort of feel as though consciousness, there are states there where you're sort of half awake, half asleep. You're coming out of sleep into being conscious. And so he says, look, is that the same thing? I mean, there's a little bit of consciousness there, right? Now, some people will dispute that way of putting it, that consciousness is dim in those cases. They might say that, this consciousness, just what it's like for you is sort of groggy or something like that. But he's making the claim that's interesting to talk about. So I'll flag that as an issue which we'll want to spend some time on in class. But back to the text. He says, we know further that the lower animals possess, though less developed, that part of the brain which we have every reason to believe to be the organ of consciousness in human beings. I think he means the visual processing, sensory cortexes. Maybe the amygdala and other emotional stuff, that kind of stuff. That's already controversial, but that's what he thinks. They do have that, by the way. So they have that brain. We think that in us is doing something consciousness-y related. And as in other cases, function and organ are proportional. So he's saying, look, if you have A really big visual cortex, you're probably doing a lot of visual phenomenology. Really small visual cortex, probably small visual phenomenology. And so we can kind of make some judgments about how conscious other creatures are by looking at their neural anatomy. You might ask yourself whether you think that helps with Nagel's question of knowing what it's like to be the bat, for instance. Okay, so I'll flag that as a second issue that comes out of this. He says, so these are proportional. So we have a right to conclude it is with the brain. And that the brutes, though they may not possess our intensity of consciousness, these are animals, and though from the absence of language they can have no trains of thoughts, but only trains of feelings, yet they have consciousness which more or less distinctly foreshadows our own. So that's his view, that animals do have consciousness, and the argument for it is based on the conservation of brain function. You find similar brain areas, but less developed. The reasonable hypothesis is same area doing roughly same thing, but less developed, so doing it sort of less well. Okay, so that's why he thinks that these are conscious machines, because it's here, so it's got to be in nature. So here's the sum, here's the punch. He says, all states of consciousness in us are immediately caused by molecular changes of the brain substance. It seems to me that in people, as in animals, there's no proof that any state of consciousness is the cause of change in motion of the matter of the organism. That's an important sentence, so let's read it again. It seems to me that in human beings, as in animals, there is no proof that any state of consciousness is the cause of change in the motion of the matter of the organism. So he's saying, look, this stuff doesn't seem to play any role. When you look into the brain and you start to try to explain why did this behavior get produced, you are led to further brain mechanisms. Say, oh, well, there is an action potential. Energy was produced. Oh, so maybe the mind produces that energy. Oh, well, actually, the energy was produced by these sodium ions and these calcium ions and these potassium ions. And those came from things that you ate. And so each thing that happens in the brain looks like it can be explained fully in terms of brain stuff. It follows that our mental conditions, returning to the text, says Huxley, are simply the symbols in consciousness of the changes which take place automatically in the organism. And that, to take an extreme illustration, the feeling we call volition or causing an action is not the cause of a voluntary act, but the symbol of that state of the brain, which is the immediate cause of that act. We are conscious automata endowed with free will in the only intelligible sense of that much abused term. Inasmuch as in many respects we will be able to do as we like, but nonetheless parts of the great series of causes and effects, which, in unbroken continuity, compose that which is and has been and shall be the sum of existence. End quote. So that's a nice little quote from Huxley there, but you see what his argument is supposed to be, that in the brain, we don't find room for consciousness to do anything. But yet we can't deny the existence of consciousness. That seems crazy because we're Cartesians, remember. So the only result is epiphenomenalism. And Huxley here is gesturing towards something which in various places has been called the causal closure of the physical. And it's related to the conservation of energy stuff, but it's different. So conservation of energy just says that, and conservation of momentum and all these conservation laws just says that whatever total net stuff you have there, you're going to have the same amount of stuff at the end. So in principle, that's not at odds with non-physical energies and spirits and stuff, as long as that kind of energy is conserved as well. Now, the problem is that when you look for it, you don't find it. The physical system seems, and that was sort of what Leibniz was putting his finger on, any given physical system seems sort of one in which All the energy is there and is merely converted back and forth, and nothing is coming in and out of it. Then you look in the brain and you find out, this is the Huxley version of it, everything in the brain that's happening has a cause in terms of some other brain state. And so this gives you an argument that the mind can't be doing anything. Here's how it goes. So you take this first premise as an inductive premise established by science over the course of a couple 100,000 years or so. And that's the claim that every physical effect has just a physical cause, that there are no other causes. There's a physical cause and just the physical cause. So if that's true, then it just follows that the mind, if consciousness is non-physical, can't do anything because, well, the brain is doing something which produces behavior, and that's a physical effect. So causal closure tells us that there must be a physical cause for that. Now, some people try to do fancy footwork and say, well, can't there also be a mental cause? Can't they both be doing it? That's what's sometimes called overdetermination. And an analogy often trotted out at this point is a firing squad. If you get shot by 4 guns, or if you're being strangled as you're falling from a building, then your death is caused by 2 things, hitting the floor and choking, or being shot by 2 different bullets. And people have said, oh, it makes sense to call them both the cause. And so, all right, that's interesting. Now, a lot of people just rule that kind of stuff out. And I would be one of those people who would be very suspicious of overdetermination. And that's what the just is doing there in parentheses. There doesn't seem, overdetermination by non-physical mental causes as well as physical causes seems like postulating things which violate Occam's razor. It just seems like more stuff than you need to do the job. You can do the job with the physical stuff. So the non-physical stuff can't be doing anything. There's just no room for it. So therefore, that's why he concludes, look, it's produced by the brain, but it can't interact with the brain in any way because science is showing us, and physiology is showing us, physics is showing us. These sciences are coming together to show us that the physical world is an isolated system, fully contained within itself, and that every interaction within that system is accountable for in terms of previous physical interactions in that system. And nowhere in that great chain of explanations do you see any room to insert some non-physical extra stuff. That's probably the centerpiece of the argument against dualism, is this idea of causal closure, which comes from the sciences. Now, the problem for Huxley, which he doesn't deal with, I'm not really sure why he didn't see the reverse of this. So if every physical effect has just a physical cause, then it seems like you could say the reverse. Every physical cause has just a physical effect. Why does he think it's okay to say that the brain produces this non-physical thing? How does it do that? You rub together 2 sticks and you produce a non-physical thing? Even if that non-physical thing doesn't turn around and do anything, it doesn't seem good enough. So this seems, again, it pushes you to the extreme. Consciousness is this kind of isolated thing that has no effect on the brain, in which the brain has no effect on it. It's this extra thing riding around that doesn't do anything. But, that's exceedingly weird, as the Smolian article in the book that we're reading points out. If you have a headache, why do you take some aspirin? Because your head hurts. Look at me, I've been sick, so I took some Advil flu and sinus. Why did I do that? Well, I think it was because I had sinus issues. My head was stopped up. I couldn't breathe. I felt horrible. So didn't that feeling horrible have anything to do with it? Huxley says no. It's all the physiology. The feeling horrible bit just kind of rides along for free, correlated with a bunch of physical stuff, but not interacting with it in any way. Now, of course, at this point, most people just kind of look at you like, what? And even after you go through all the physiology and you try to actually make the case as forceful as possible, most people just go, Epiphenomenalism is weird, man. And of course, Huxley knew that. You know how many incredulous stares he had to put up with in his lifetime, I'm sure. People just look at him like, what are you talking about? This is what he has to say. Quote, as to the logical consequences of this conviction of mine, I may be permitted to remark that logical consequences are the scarecrow of fools and the beacons of wise men. The only question which any wise man can ask himself, and which any honest man will ask himself, is whether a doctrine is true or false. Consequences will take care of themselves. At most, their importance can only justify us in testing with extra care the reasoning process from which they result. And of course, that's right. He's exactly right about that. Everybody who's ever said anything at odds with the norm of the time had said something which seemed wildly implausible. The earth is in motion, wildly implausible. Now, we got some evidence for that. And of course, we want to carefully examine it, see if it's true. But just because it's really wacky doesn't mean it's false. And he's saying the same thing here. The argument from, hey, that's crazy, man, doesn't do anything. It just means, oh, I guess you don't want to talk about my argument. So maybe it's false that epiphenomenalism is the way things are, but we have to say how we get around it. Now, of course, the sort of obvious answer is going to be coming next week. Well, one way you could get around it is just go towards physicalism. Like this dualism thing seems to be really messing us up, because now this is the second time that we've been through this stuff. We've started from physics and we said, aha, it looks like epiphenomenalism. We started from biology and we ended up with, it looks like epiphenomenalism. So it looks like maybe we got to move on, accept epiphenomenalism or start looking at materialism or physicalism. But of course, that's too quick, because we haven't met the other major development here, which is the transition from Newtonian mechanics to quantum mechanics. The transition from the science of motion described by Newton's equations to the science of motion described by quantum mechanical equations, which are a different beast altogether. And of course, we've been discussing this for a long time, and we're suddenly shifting gears here. And quantum mechanics would require a million years of study on its own to even be able to say anything interesting about it. So it's kind of a, we'll mention this because people talk about it, but obviously we're not going to be able to give it the kind of attention that it needs. Someday I will try to do something on quantum mechanics for the philosophy of physics class that I do, like I've been mentioning all along. But there's tons of stuff on this stuff. It's been over 100 years that people have been developing this, or coming up on 100 years, I should say. I guess in the 2025. It doesn't matter. Okay, so, but going back to the time. So here's James Clerk Maxwell, who probably the greatest mathematical physicist of the 19th century, prior to Einstein and those kind of people, who really taught us a lot about Maxwell, he taught us about his own equations. No, he taught us about electromagnetism. And, we're not going to go into the details of this, but the big problem of the time was how you make sense of electricity and how you make sense of magnetism. They thought they were two fundamental forces in the world. So the gravity had been clunking along pretty good now. Euler's equations were doing some good work, and all kinds of kinetic energy stuff, and all that stuff is wonderful. But there's, electricity is important and magnetism is important. So people were working on trying to figure out what was going on with those things. And this is really the development of the idea of a field, and where the idea of the electromagnetic field comes from Maxwell's work. And so Maxwell's equations are really put together in their canonical form in the 1850s or 60s. I think it's 1861 or something when he sort of publishes his famous paper, although don't quote me on that, and it doesn't really matter. But we should know that the equations that he comes up with, don't come out of a vacuum. He's working, refining the work of people like Gauss and Ampere and all these other people, and more fully we'll talk about that. But he comes up with 4 equations which unify the forces of electricity and magnetism into one, the electromagnetic force. Now, we'll look at the equations just because it's fun to look at them. So here they are. There's 4 of them. 2 equations for electricity and 2 for magnetism. So the E is electricity and the B is magnetism. And of course, this is one way of writing down the equations. And this is the way they're usually trotted out in. This is the differential form. You could write them as integrals. And you would get different, but they look a little more clunky. These ones people like because they look simple and elegant, and they look all fancy. Sort of, the idea is that you want something nice like F equals ma or E equals mc squared. And of course, you don't get exactly that, but these curl dot operators or curl x operators are close enough. So anyway, of course, writing them down is just convention. You can do it any way you want, but understanding the relationship that these things are getting at is really the significant achievement. So let's take that second equation first. It says curl dot b equals 0. Now that's, you know, a fancy way of mathematically expressing the idea that magnets don't flow. There is no magnetic current. And so all of these things are describing the sort of lines of force emanating through the field generated by electricity and magnetism. And basically that equaling 0 right there means that the line of force isn't straight. It curves back and goes back to where it emanates from. And if you ever looked at a picture of a magnet, that's how they draw it. It goes from the north to the south. That's the line of force, north to the south. And that, you know, is different than the other thing up there, which describes electricity, the curl dot E thing there, which tells you it's not equal to 0. It's equal to something on the right-hand side there. And that tells you that you can get flowing current, electricity moving from one place to another. The line of force is going to be a straight line. It's moving. It can go from here to there. And that's why current flows and magnets don't flow. So, and that also is related to another interesting thing, which I'll just mention, which is the fact that we have positive and negative charges, but we don't have positive and negative magnets. So you can find one magnet with a north pole and a south pole, and the line of force runs from one to the other. But if you break that magnet in half, the top part doesn't just become the north part, and the bottom part doesn't just become the south part. You get a new magnet with two new north and south poles. So there is no just positive side of a magnet, and there is no just negative side of a magnet, in the same way that you could have a positive charge without a negative charge and a negative charge without a positive charge. So that's been one of the fundamental mysteries of Maxwell equations, is why that second equation doesn't look like the first equation, but for magnetism. Why isn't there a symmetry there? Seems to be a symmetry everywhere else. That's led to this quest for the existence of what's called the magnetic monopole, which is super interesting. But we haven't found it yet. So, you know, there's that. Now, so those tell you the two fundamental things I just said. One, that current flows, and the other, that magnetic current doesn't flow. It's doing something else. Now, the bottom two equations tell you the way that magnetism and electricity are related to each other. And basically, they tell you that by generating a magnetic field, you get an electric field. That's what the bottom equation there. So the electric, the B there is related to all of that stuff in joules. That's energy on the other side. So you see the bottom one. The third one has E on one side, B on the other. So it's relating electricity to magnetism. Same here, magnetism, electricity. So basically what this says is you can make electricity with magnets, and that's, you know, the source of all of our electric power that we use. It comes from understanding these equations. If you generate a giant magnet and move it around, it's going to generate an electric current. And that's what those equations tell you, is how much that current's going to be generated. And so this is all very interesting. But as these equations really came to be understood and they were used, and, you know, you could go and take your advanced physics class and start learning how to actually calculate some of these things, and that's all very nice stuff. But the notion of a field really came to be implanted in physics in a deep and permanent way. And it's really something that we can't really, we don't know how to do without it, or at least it's not clear how we get around it. But fields are very strange things. So let's talk about what a field is. So let's suppose that you just have some object. This object has a mass, it's denoted by M, and I call it M2 because it's the second. My animations were whatever. So there's this object. Now a field is defined in the following way. A field is a physical quantity that has a value for each point in space and time. So you can think of fields as permeating all of space and time, and for each point of space and time, there's a value associated with that space and time, a vector value or scalar value, depending on the kind of field that you're talking about. It can be a number or a set of numbers. That's an ordered set of numbers. So that's the difference there. So, to help us here, we imagine this space-time grid over everything. So this body here is going to create a gravitational field. And what that means is that in every point in space around this body, there's going to be some physical quantity, some numerical value, some vector or quantity that we can say represents the force which would be applied to an object were it there. So for instance, suppose you have this object located that R far away. So there's the R there. So you can see that we're setting this up for Newton's law of gravity here, because that's what you get out of this. So now the gravitational field, and remember I switched from talking about electromagnetism to gravity just because I think gravity is a little bit easier to wrap your mind around since we're more familiar with it. Electromagnetism is a little bit harder to do and more advanced. So, but here the gravitational field is simply a list of numbers associated with space-time points. The numbers represent the force which would apply were an object placed there. So for instance, here's this one. And we know from Newton's equations that the force applied to that object is going to be equal to G times the two masses divided by the R squared. So that we could calculate that. And then we could find out how much force the square is applying to the circle and vice versa, the gravitational force. And basically what that means is that this thing will move in a certain direction as a result of being in the gravitational field. And this idea, this is what's called the classical field. But this idea has blossomed into what's called quantum field theory, which is the most well-confirmed mathematical theory of physics ever devised by human beings. It's quite astonishing how good the math works. It treats all of the fundamental particles as fields. So there's a field associated with each fundamental particle, like the electron field, the proton field, and all those things. And then there are fields associated with each fundamental force, gravitational field, electromagnetic force field. And each of those fields has an effect on the particle fields, and they interact in various ways as described by the math of physics. So, and in particular, they interact in the way described by the quantum mechanical laws of motion, which it turns out are very different than the classical Newtonian laws of motion. And of course, again, like I said, this is a philosophy of mind class, not a philosophy of physics. So we don't want to spend too much time on the physics, but in order to understand the mind's place in nature, you have to understand nature a little bit. And of course, quantum mechanics is extremely hard to understand. We've been developing it for 100 years or so. I say over 100 years here. I guess I'm dating the development of quantum mechanics to Einstein's paper on light being quantized. But really, the canonical form of quantum mechanics doesn't get set until like the 20s or so. And then that's what sometimes people call the old quantum mechanics, and then quantum field theory, quantum chromodynamics, and these other weird things. Those come later. So we've been working on this for a while. Quantum mechanics is not new anymore. It's something that we've been working on, but we still don't understand it. And that's one of the weirdest things about quantum mechanics, is that the math is wonderful. People use it all the time to make predictions, which they go into the laboratory and verify. But we don't know what the math means. We don't know anything about the right metaphysics which go with the math. And of course, that gives some people what they perceive as an opportunity. So some people have argued that there's this important thing called the collapse of the wave function. And it's a big mystery in physics how we deal with the collapse of the wave function. So some people have said, well, maybe consciousness is importantly involved. And that's what we want to examine in the time that we have left today, is the way that people have thought this might work, and the way that it probably doesn't help very much. That's where we're going to end. Okay, so as I've said already, quantum mechanics is too weird. And there's a mathematical formalism, and then there's some like weirdness. So I think that Schrodinger had it right when he thought, look, the way to get at the weirdness was simply by talking about this Schrodinger's cat thing. So, and then remember, this is not supposed to prove anything. The Schrodinger's cat thought experiment is supposed to be a way for us to sort of fully come to understand what's so weird about quantum mechanics. So the setup is probably familiar. You put the cat in the box. Remember, this is a thought experiment. No cats and no real boxes. Thought experiment. So you put the cat in there. And also in there is a deadly poison. And the poison is in this little area, which you have to press a lever. A lever has to open. A door has to open to release the poison, let's say. And that door is controlled by this device. Okay. And the device is connected to a radioactive substance, which, just to make things easy, has a 50% chance of decaying in the course of a given period of time, let's say an hour. Okay. So now this is getting at what's weird about the quantum mechanical stuff, is that the laws in their most fundamental form don't give you actual outcomes for experiments. They tell you the probability of finding certain outcomes if you do it a bunch of times. And it's in no small part, that probably is one of the weirder things about the math of quantum mechanics. If you look at F equals ma, there's nothing probabilistic about it. It's F equals ma, and then you can go, okay, the mass is n, and a is m, and you get an actual number. And then you can test it. But quantum mechanics says not F equals ma, it says 50% of the time F equals ma, 50% of the time F equals 2ma. I mean, I'm making that up, but you get the idea that it tells you only probabilistically. But these probabilities are always verified. You do it enough times, you get exactly what's predicted. So that's weird. Now imagine this piece of radioactive substance. Suppose that we know that it has a 50% chance of decaying. So what that means is that there's a law which tells us that after a certain amount of time, there's a 50% chance that the thing has decayed and a 50% chance that the thing hasn't decayed. And if you look at the equations, you actually see both it being decayed and not decayed. And the math is telling you that somehow, both are happening or neither is happening, and it's a combination of the two. Now, people have interpreted that to mean that what the laws of quantum mechanics are telling us is that before you look in the box, it's in this weird in-between state, what's sometimes called superposition. It's somehow kind of both. Now, why would you think that? Well, because the law doesn't tell you it's one way or the other. The law just says 50% chance it happened, 50% chance it didn't happen. And in fact, the math tells you something weirder. It did happen and it didn't happen, and they combine together to give you the probabilities. That's what's called the wave function. It tells you how the probabilities, this probability wave, is distributed. But of course, that's not what we find when we open the box. We never find the cat in this superimposed state of being both alive and being both dead. We never find the poison both released and not released. We find one or the other. Now that, in a nutshell, is the measurement problem. The laws tell us that, it's all this probabilistic stuff. But when we look, we only find one definite outcome. Now, one question is, well, when you look, why'd you get that definite outcome as opposed to any other one? Now, of course, if you do the experiment enough times, you'll get both of them. And so the probabilities hold up. But on any given time, why this one versus that one? And the laws don't tell you. They just say 50%, 50%. So some people have said, look, this is just too weird. The laws say that it's both and neither at the same time that it's been released, that the cat is dead. The laws say that before you look, that's all you can say. But every time we do look, it's one way or the other. So what makes it the case that only one outcome is the one that we see? That's one question. How does the probability wave collapse to one actual thing happening? That's the collapse of the wave function. How does that sea of possibilities collapse to one actuality? The other question is, what's really going on inside the box? What's really going on inside the box before you look? These things are the measurement problem. The math works well. It tells us this weird thing. Every time we look, we see something opposite of that. What makes that the case? Now, of course, this is the old quantum mechanics, talking about Schrodinger's cat and a wave particle dual complementary. See, I can't even say that. That's why people say superposition nowadays. So these ideas have been updated, but they have not been disproved. We just still don't know what to make of it. And of course, if you know about the double slit experiment, that really is the ultimate kind of example of what's going on here. But the light seems to behave like both a particle and a wave, depending on like how you ask it, which is very bizarre. And we don't know what to say about that at this point. And so I brought out, so that's one thing that's weird. Here's another thing that we've already mentioned, which is that it seems like on any given case, any given trial, there's no cause for why the experiment comes out one way versus the other. If the law tells you you have a 1 in 4 chance of this happening and a 1 in 5 chance of the other thing happening, and then it happens one way versus the other, the laws don't tell you what mechanism makes it come out that way. It looks like it's just truly deeply random. This is what caused Einstein to shout, God doesn't play dice. It's not random. There's got to be some mechanism. So that's weird, and people don't know what to say about that. Now, there also is this thing I'm sure you've heard of called the uncertainty principle, which comes from Heisenberg. So and not the Breaking Bad Heisenberg, but the physicist Heisenberg, not the chemist. So the uncertainty principle is a certain claim about measurement. And what it claims is that the more exactly that you know one kind of value, the less exactly you know another kind of value. Notice that's about measurement. So for instance, certain pairs of properties seem to be related in this way. And the earliest discovered one, although there are others, it turns out, but the earliest discovery was that the position and velocity of a fundamental particle are related by this uncertainty principle. Now, what does that mean? Well, if you think about Newton, F equals ma, the a there is a vector. It's acceleration. Acceleration is speed plus direction. That's the vector component you need. It's not just a number. It's an ordered set of numbers which tell you something. So it tells you how fast it's going and in what direction it's going. That's acceleration. So F equals ma will allow you to calculate the acceleration of any given object at any given time if you know its mass and the forces acting on it. So that's quite nice. And you can determine to know its acceleration, you have to know its position, where it is, because that's going to tell you where it's going to be later. And you have to know in which direction it's heading. That's the acceleration. So you need both of that information to do F equals ma. And it turns out that for the fundamental particles, that you can't get both kinds of information. You can only get one or the other. So you can either know where the thing is, but not which direction it's going. So you can get its position, but not its velocity. Or you can get its velocity, which direction it's going, but you can't know where it is. Now, and really it's the more exactly or precisely you know the one, the less precisely you know the other. So it's, you can to some extent know both, but you can generally know them both, but if you get very precise about knowing exactly where something is, then you can't know in which direction it's heading very much at all, if at all. Now, why is that? Well, that's weird, but it's required in order to make sense of these kinds of predictions that the math are telling us. So the math tells you that if you look for a certain electron, you have a chance of finding it anywhere. Now, where it will be found is sort of more likely to be a given certain area where you might have thought its classical location is. But there's a non-zero chance it could be anywhere. So this is super strange. You open the box, you look inside, there's the electron. You close the box, you open it up, it's not in there anymore. How did it get out? Well, we don't know, but that kind of stuff happens all the time when you measure things. You look, it's there, you look again, it's gone. It's somewhere else. And that somewhere else could be anywhere in the universe. Now, 95% of the chance it's like in the box. 95% of the time it's in the box. 1% of the time it's like close nearby the box. But some non-zero percent of the time it could be anywhere else, on the moon, in a different galaxy at the center of a black hole, which gives rise to the information paradox, if anyone's keeping track of physics nowadays. So this is a very super weird thing, that it seems like it could just go anywhere. But if that's so, then you can't know which direction it is. So you can know it's there in the box, but you can't know where it's pointing at because it could be anywhere. And if you had that information, you wouldn't be able to measure it as being like, on the moon or something like that. Now, of course, if you don't understand what any of that means, that's fine. This is all very deep and complicated stuff. The point is, no one understands what any of that means. These are things that we discover, though. The uncertainty principle is a consequence of the mathematics. And then finally, one other weird thing I'll mention is entanglement. And again, each one of these things are things that we observe, but we don't know how to make sense of exactly. So it's not as though we know that these things are this way. It's that the math is telling us one thing, what we observe is another thing, and we don't know how to make sense of that. And entanglement, of course, is one of these things. And the conservation of momentum is the way that Einstein thought about this stuff. And he's really the first person to kind of bring out this weirdness. And then some people think anyway, it's been experimentally verified. So the idea here is that in Newtonian mechanics, it seems like two distinct balls can't interact with each other if they're far enough away. And Einstein really didn't like this uncertainty principle. He thought there's got to be some way you can know something about the cat or something in a similar situation. And the conservation of momentum seems like a good place to look, because what that tells you is that if you know the momentum of a certain object, and if the two started in the same way, you can apply the equation P, momentum, equals mass times dv over dt, the normal derivative there. And so you can figure out what the momentum of this one particular object is. But since these two things started out as a total system, and if they're moving in opposite directions from each other, then by measuring the momentum of one object, you could come to know the momentum of the other object. You could know something about which direction and how fast and stuff that it's going, because P equals m times dv over dt. So you could figure out some stuff by measuring one particle. You would know something about the other. And so Einstein said, see, that's weird, because the quantum mechanics tells you that the other particle that you're not measuring, not being affected in any way by you measuring this particle, it shouldn't have any determinate properties because you're not measuring it. And according to the math, it's sort of in this indeterminate state, this superposition. But conservation laws also tell us that by measuring this thing, it should have some definite property. So Einstein said, look, you can either go one of two ways. Either quantum mechanics is wrong and the thing really does have some determinate property that we just don't know about, or it seems like measuring this thing right here has an effect on that, even though they're separated. And a lot of people think that, well, the second thing is true, and that's called entanglement, that somehow these things are have an effect on each other, even though they're separate. That's weird. Okay. Now notice these are all sort of things, empirical stuff. What we're supposed to say about this stuff is still a mystery. So let me just throw these things up here. I don't like how it gets. I guess I should have changed for this slide how it dims out, but I wanted you to see all four at once. These are sort of four of the more popular interpretations of quantum mechanics. And these aren't the only ones. So on the one hand, we have what's called the Copenhagen interpretation. That's kind of the standard one, if there is a standard one. On the other hand, we have what's sometimes called the hidden variable interpretation. I think maybe that's similar to the Bahmian interpretation, on which you interpret quantum mechanics as having fundamental particles that are kind of Newtonian, but then these particles behave in weird ways. They behave in quantum mechanical ways, but they aren't merely just these wave function things. Then there's the many worlds interpretation, which claims that for every possible way the experiment could work out, it does work out that way. It's sort of a branching. You roll the dice, 6 different worlds result, one in which is 1, one in which is 2, one in which is 3. Whichever one you happen to be in, determined by what you see. That's a weird claim. And then there is this other view called objective collapse theories, which claim that, the reason the wave function collapses is some objective feature of the math. And sometimes people point to decoherence, like when you get things big enough and wet enough, and they're sort of approaching macroscopic levels, the wave function just the math just tells you, boom, it collapses into one versus the other. Now, I don't really know, and by the way, the point of this is that no one really knows which of these 4 interpretations are correct. But the Copenhagen interpretation makes the claim that before you do any measuring, there is no fact of the matter about which of the ways the things are. And that only doing the measurement produces the thing being that way. And if that's the standard interpretation, and these other ones are outliers, then the standard interpretation seems to involve measurement. And some people have said, aha, you mean measurement? Like when a conscious observer looks at something? And so maybe after all of this rigmarole, all of this hullabaloo, maybe we come back to where we thought we should have been in the first place, which is that consciousness makes reality. Some people have said that in response to this, that it's sort of the idea, going back to idealism, that reality isn't there until you observe it or look at it. And in that sense, that sounds very Berkeleyan. So some people have said, aha, you can see this quantum mechanics as relating to that. Other people have denied that. But it's a very suggestive view. I see I didn't have the full slide out here, but the basic point is that if you're looking for some reason why out of the math telling you there's all these possibilities, but yet only one of them is what's measured, what's the reason for that? Well, according to this view, it would be consciousness is doing it. Now, there are some problems with this. One thing you might think this has something to do with like a higher order view. You need to have this awareness of what's going on in your own mind in order to make it real. And that's interesting. You may think this has something to do with intentionality. You have to be conscious of the thing there. But you might wonder whether this is sort of anything at all like our normal view, that when I feel hunger, that makes me think I'm hungry, and those things are involved in me wanting to get food. Yes, there's a whole story about certain levels of various chemicals in my blood, and there's a kind of mechanical valve in the stomach, and when it goes below a certain rate, a certain lever's pushed and a signal is sent. There is that story, but there's also like I feel hunger. And doesn't that feeling of hunger do anything? It's not clear that all this quantum mechanical stuff gives you anything like that. And this is a point that David Chalmers has made in his book on this, 1996 book, Conscious Mind, where he briefly talks about this stuff. It's just, and I think he's right. It's just not at all clear that you get anything, which was the common sense view, that like my feeling of pain causes me to do something, that my seeing of the red or smelling of the scent, the actual experience of that plays any role in producing my behavior. Instead, what we get is this idea that, well, consciousness is involved in making measurements of the world, and that sort of brings the collapse into an objective state. That doesn't sound anything like mental causation, like normal mind-body interactions. Now, one of the things that you might wonder about at this point is now, one other thing that you might wonder about is whether the only kind of measurements that matter are the measurements made by conscious observers. So it's not clear that being conscious, as opposed to just making a measurement, is really what's doing the work here. And there's a long story that you could tell about the delayed choice quantum eraser style experiments, whereby it seems like the sort of message that we're getting is merely collecting the information and having it accessible is what causes the problem. Even if we never look at it or never consciously observe the measurement being made, the mere fact that the measurement was made and we can get to it seems to be enough to make these kind of quantum mechanical things relevant. And so some people have said, look, it's just an accident that measurements is, as we do it, is done by conscious observers. But you could have machines do measurements. You could have unconscious alien beings doing measurements. And that would be enough to get the measurement problem and all the quantum mechanical stuff. So at the end of the day, I again think David Chalmers kind of sums this up nicely when he says, yeah, consciousness is weird, and quantum mechanics is weird. So maybe the two weird things hang out together. I think that's a kind of natural thought that people have. But when you go through and look at all this stuff, it's not clear that consciousness does anything important for quantum mechanics. And not only that, but you really need to put a lot of weight on one interpretation of quantum mechanics out of many of them. So the many worlds interpretation is getting a lot of attention lately. It may ultimately be wrong, but it seems importantly related to the multiverse hypothesis. And the multiverse hypothesis is getting some support, not only from string theory, but from the recent discovery of gravitational waves in space-time, which inflationary theories predict. Inflationary theories also, by the way, the math of them predicts multiverse. So some people see an important kind of pointing in the direction of something like a many worlds interpretation. Whereas other people think, look, the Bahmian interpretation is good too. You have these kind of classical particles. They behave in quantum mechanical ways, but they're still classical particles. That's hidden variable kind of interpretation, very much still alive. So it's not clear what we're supposed to say here. The only thing we can say is that while not ruled out, substance dualism faces a serious challenge from mental causation. We want to keep mental causation. Epiphenomenalism should ultimately be avoided if at all possible. Now, it may not be possible, but we still have some options. We haven't looked at neuroscience in a lot of detail, though we did some physiology, but maybe the new neuroscience can help, or maybe computer science can help. But ultimately, we're going to come back to these ideas because we're going to meet the contemporary dualists who take their starting off from a lot of these points. And contemporary dualists think they have a way out of this epiphenomenalism problem. And so we'll come back to that after we look at the materialist solutions to the problem of epiphenomenalism.